Can you hear me? Hello?
Yes, sir.
Okay, I am
Yes, sir.
starting.
Good afternoon, sir.
हाँ, गुड आफ्टरनून अभी हुआ नहीं, 12 बजने के बाद होगा भाई, समझा?
यस सर। सर अभी पिछली क्लास चल रही है, सो थोड़ी देर और रुक जाइएगा।
अच्छा
सारे
ठीक है,
बच्चे नहीं आए हैं।
ठीक है।
Good morning, sir.
Are you ready? Hello.
Yes,
Yes,
sir. Sir.
Okay. So today I'll start metric space. I think it is, you can see that, right? Whether it is note 8 or something, metric spaces. So that let me start with this. In the first page, basically I wrote the motivation that what, first of all, what is the metric space, and before that, why you should study metric space. Question is, why should we be, why should we study metric space? That's a question. Okay. Well, before answering this question, look, you have done so-called little bit real analysis. Even if your real calculus is part of real analysis. Look, what real analysis means? It means analysis on R or Nyan or to the power n. Look, when you had functions of several variables, you did analysis here. And when you are having only function of one variable, you did that. So particularly, you have studied functions like this, R to R, or maybe something interval. But that is also subset of the real line. Or you have done something like this. Functions of several variables. Okay, like this. That you did. So now look, all these things, now if you go back, even if your calculus, derivative, continuity, first you looked at continuity. So I'm not going, I don't need to go to the derivative. It continuity will give you the enough motivation. Look, if you go for the definition of continuity, so-called epsilon delta definition, this is the real definition of continuity actually. Okay. Here I should tell you that when you write for continuity like this, So this is not the definition of continuity. This is just a notation to indicate the continuity. This is not definition because this doesn't explain what does it mean. Okay, so that epsilon delta is the real definition of the continuity. That you should understand now. This is second one. When you write this, this is just notation. It follows from the definition of continuity. It is just it is not definition. Also here you should, once you have it, continuity here for the real line, look what continuity gives you. That is very important. Why people are interested in continuity? FC, look, FC, you can write this. Now forget in between. Now look here, if you think limit and f are two operations. Limit and f, function and limit, two operations. Now look here, limit is the first operation is f, then limit. Here it's opposite. Limit is first operation, then f. That means limit and f, that they are commuting. Limit and f, these two operations are commuting. That means limit f, you are getting f of limit. Okay, so this is very important. That is actually the use of continuity. Often even in applied math, in some calculation you do it, you keep pushing limit out in outside or inside at your whims, but that you should know. Some condition must be there. Particularly you can do if you have the continuity. Otherwise you are not allowed to do it. If you do it indiscriminately without thinking like this, then you may reach the point of contradiction, like 1 equal to 0. Okay, so that you'll have to be careful. The continuity's biggest contribution is this. Now, so that you have done analysis on the real line, but the point is that this even epsilon delta definition you did for this, or suppose this is a function. Go back to your undergraduate study and that. Here is anybody in your class from St. Stephen's College? Is anybody there? No. Okay. So that look this, that here when you are defining epsilon delta definition of continuity, use the concept of distance actually between 2 points. To 2 points. Otherwise, if you look and again go back, if you have the distance, everything epsilon delta definition was defined, the definition of continuity in terms of basically distance. And look at the compare the definition of continuity here you got and definition of continuity here you got. You see that if you just look at the distance, the definitions are same. Definition is the same. Though they say it here domain is different, but definition is same. Definition only depends on the distance between 2 points. Now, when you are doing analysis on the real line, look, first of all, look at this. R with this mod. Mod actually gives what? When I say x belongs to R, mod x means distance from distance between x and the origin, 0. Okay. Whereas this means distance between the points between x and y. Okay. Of course, I could consider that there should be direction. Actually, it is distance from x to y, and this is distance between y to this distance between y and x. Like if you have point here, if you want here, once you are mapping going to this x to y, so you are stopping at y, that means y minus x, this distance x to y, and when y to x you come here, then you are coming this way. Then this one, y to x, sorry, x minus y, y to x, yes, this one. Okay, one is the distance from x to y, other one is the distance from y to x. But you know, it doesn't make a difference, it is same. It is expected. Okay, so that it did this. That is between 2 points you got a distance. That is the one thing you got, and that this thing is same. These are so much guaranteed and that you never bothered in your proof to check, and that it is up, you never bothered to think about it. Okay, the second thing is that we got, if this is 0 distance, if and only 2 points are same. Okay, that also you didn't bother, though all you are having that occasionally without realizing that you are using it. So that this one you got, this one you got. But what is the most important thing while doing manipulation, calculation, you are using it? That is, look what you used. You used this thing. X minus y, you wrote this x minus z plus z minus y. Basically, it is called the triangle inequality, because triangle inequality says what? Look, if A, B, C you have, okay, that means you can call it x, y, z. It says that what? Look, this is x minus y, this is this side, okay, the distance, whereas x minus z is this side, distance, and z minus y this side. So this is in the triangle in the high school geometry you did, the sum of length of two sides is always greater than equal to sum of the greater than equal to the length of the third side, right? That is the this. Okay, right here x minus y, this one, this is, if you take the length x minus z, this is AC. This I say the line segment, not the entire line. Line segment AC, its length you are taking, and BC. So this gives you the so-called triangle inequality. If you, whatever calculus, real calculus or analysis you did, you go back to your proofs, you see that any good result, you must have used triangle inequality. Okay, if you have not used it, then it is not a good result. Look, if you have not used it, is the two things. That means you are using another result in which you use triangle inequality. Okay, directly or indirectly, that means directly or indirectly, you will be using, or indirectly, you will be using this triangle inequality. Indirectly means you are proving a result. To prove that result, you are using another result. That result uses triangle inequality. In fact, if you don't use triangle inequality, you are not going to get a good result. So that triangle inequality is the most important. That actually you try to manipulate, you try to use it. On the other hand, two properties, what I said, that distance between x and y equal to y minus x, that means length A, these are same. Okay, and x minus y equal to 0 if and only if x equal to y. Look, so that you are having the distance concept, and if you use this distance concept, can you use it intelligently, then you could see that many things of what you did for functions of several variables and functions of one variable, you could study them at the same time. That means without repeating it. So the idea of the metric space is that, okay, here when you study metric space, ultimately we are going to real analysis means analysis on R. Okay, and here after knowing about enough about metric space, then we do analysis on metric space. Why it is called metric, that I will tell you that. That means here on R you are doing, here initially you are having a non-empty set X, arbitrary set X, okay, and that on you are giving a concept of distance, D, concept of distance. This is initially is called a metric. So metric is a generalization of the idea of distance. So it's a pair. Look, here you had a pair also. It is not only R. When you are doing analysis on R, actually you are having this pair. You are not only having the numbers, real numbers, you are having this with the concept of this distance. Similarly, in GAL, when you try to generalize it, then you will have all these properties here and with the concept of distance between 2 points, okay, and then this pair will be called a metric space. I'm going to define it before that. And not only X is just a set, xt. Now look what that means here. When I gave the concept, look, this is actually function from R cross R ordered pair. This function I am denoting by this mod. That means if you have x, y, Cartesian ordered pair, your function was that. Okay. If you call it to feel comfortable f, that means f x y. Okay. Actually there should be 2 brackets, but we do not use it because it's a function of only this point and that bracket. That you are taking x minus y. समझ गया? So actually you are having this function from R cross R to this, and which function was satisfying this, that this is 0 if and only if x equal to y and x minus y equal to y minus x for all xy. Okay, and finally triangle inequality. The same concept I am going to imitate this thing. Look, so that suppose I have a non-empty set and suppose I have a function from here. Now look, when I give this function, it is not only a real number, it was a non-negative real number. Okay, so that you can write here, but then you'll have to put this condition. This is a function. Suppose I have such a function. What I should have it. Suppose I have a function a, that fxy non-negative. This is greater than equal to 0 for all xy belongs to x. Look, xy belongs to x means xy belongs to x cross x. Okay, so this is same thing. Okay, b, fxy equal to 0. This it was understood that I was taking on, some people write here non-negative reals. That then you don't need to mention it because function is going to non-negative reals. Since I have not mentioned it, I am writing it to emphasize right now. Okay, to emphasize right now. Okay, so fxy equal to 0 if and only if x equal to y. Function c fxy equal to fyx. Look here, since it's a x cross x, so xy belongs to x. That means x belongs to x, y belongs to x. So this also makes sense since I am having the same set x. Okay, so here I am saying C for all xy belongs to x. D, look, this I can put here or else I can put here, that I told you if I write r plus. Okay, and D, that triangle inequality, how to write? Okay, I can write this one. In between, I am putting one more point so that I have this. Then triplet, you need a point, triplet, 3 points. For all x, y, z belongs to x. Got it? So this is D is the triangle inequality. Okay, right? This you got. But usually you don't write f. Okay, because I am telling you f is called a distance function. Distance function. It's called distance function. So we prefer, instead of f, we prefer d. Okay, then you can see that if I now in place of f, we are putting d now. That means distance between 2 points is always non-negative. That means distance between 2 points will be 0 if and only they collapse. They are same points, x and y. And d, distance between x and y is same as distance between y and x. And this is triangle inequality.
Sir, what is capital X here?
Capital X. Capital X is the set,
Yes.
an arbitrary set. I'm
Sir,
taking
is it
arbitrary set.
subset of real number or anything
No,
else?
no, any arbitrary set. It is arbitrary set.
Okay, sir.
And that d function, I'm saying it may not exist. If it exists, I'm putting the conditions. X is any set, any arbitrary set. That's the
Any non-empty set.
yes, any non-empty set, any non-empty set. That's why we're trying to generalize the concept of the distance. Okay, so that the distance between 2 points, so actually it has to be a function on x cross x, right? So that exactly I'm doing. D. First I started with a function having some property. Then I said, since it is actually our well-known distance function, then instead of f, we call it d. Okay, so that look here, I can, if you use this notation, r plus, this is non-negative reals. Alpha belongs to r such that alpha greater than equal to 0. Non-negative reals greater than equal to 0. Okay, then if you take this function and take x is a non-empty set, suppose it satisfies, suppose you have a function x cross to x to r plus, then first condition I don't need to give because I am already taking my range r plus. So satisfying this condition, now I will write 3xy equal to 0 if and only if x equal to y. B, dxy equal to dyx for all xy belongs to x. C, dx. Okay, I could take that, no problem. Any point z, just you are introducing z, inserting z in between x, z, zy. Z can be anything. Okay, right? So if you have these 3 conditions satisfied, it need not satisfy. If it satisfies, then D is called a metric. Then D is called a metric or distance. Some people still call it a metric, a distance. But distance usually we do it, preserve it from the real line or complex plane. D is called a metric on X. Okay. Look, in the definition 1, I have said everything. Okay, so that you can read that. That's not a problem. Okay. Now, this is called a metric on X. Okay. And then now look, this pair. This is called a metric space. Look, if you just write X, S is the set. X is not a metric space. For a metric space, you need this thing metric. So a metric space is a pair, a couplet. Okay, XD. Sometimes you say let X be a metric space. It is understood then that there you are considering a metric D on X. Okay, informally often you say let X be a metric space, but then actually you are having this. So that XD is a metric space while X is a set and D is a metric on that. So that there are three things: X, T, XT. Okay. When you write this way, that is actually the complete thing description of the metric space XD. Okay. In fact, on a non-empty set X, you can have different metrics. So you can have different metric spaces. The same set X. Right? Even on R, I can give you that. Look, R. Let me tell you that. R, you have this is called the usual metric. That means you are giving this. Okay, this is called the dxy here. This is called also usual distance metric. Now you should check whether if I give this thing dxy, xy belongs to R, only R I am considering. If you give this, check that. Okay, makes sense. Given x real number, I am taking tan inverse x, arc tan x, and tan inverse y, and then I am computing their distance. See, this is the usual distance, but here it is being defined by this way. Okay, so think about this. Check. T is a metric on R. Look, this is not the usual metric, though I am defining through usual metric. In fact, one metric can give you another metric. That's a very simple thing to that. So check this is a metric. In fact, you could think about this, whether this is also a metric. They say why I have taken arc tan. Okay, I could take this thing also. Okay, check that if it is a metric. Okay, now not only that, so that here you are getting other metrics also on the same set X. So that's why you just say this is a metric, it doesn't make sense. You'll have to tell me that what metric you are considering. Okay, in fact, if you have a metric D, I think it would take alpha greater than 0, a real number. Then alpha D is also metric. How will you define alpha D? Alpha D will define just this way. Multiply D by alpha. Alpha you are picking up and keeping it fixed. Alpha strictly positive. So it doesn't become everything 0. समझ गया? So that if everything becomes 0, then it will be a metric, because then any two non-distinct points may have distance 0. So that alpha greater than 0, if you take alpha D, this is also giving a metric. So that on a non-empty set X, you can have infinitely many metrics actually. Infinitely many metrics, because if you keep changing alpha, you get another metric. Okay, so that you should know. That means when you're talking about a metric space, you need to talk about this pair X, T. Okay, got it? Now the thing is that, so first I have given you a lot of examples in that you should have the examples. Example 1 is the standard example. Okay, and now example 2 I have given, that you did, but I do not think you got this thing. Example 2, I have taken Rn, that is the functions of several variables to do it, dxy. X is actually this point, xn is yn yn. Then dxy, you have defined this. You have taken the square that I have written half on that. This gives a metric. But when you are going to prove something is a metric, if you are checking, only thing will give you the trouble, that is triangle inequality. Okay. So how to prove triangle inequality here? So I am leaving it an exercise. Look at that, triangle inequality. How to prove it? So there, this I am giving you an exercise. Okay. Right. Before that, let me comment two more things. Okay. I have put the question in page 55. How to prove the triangle inequality for the Euclidean distance on Rn? Look, this is called again the usual distance on Rn. Like this is the generalization of the distance on R. Only n greater than equal to 1. Okay, so that this is also called usual distance. Usual distance or called Euclidean distance. Reason is this distance gives you actually the Euclidean geometry on Rn. Okay, if you have problem, you can still think about n less than equal to 3, so that you know what is the geometry. Okay, so this actual distance gives you the Euclidean geometry. That's why it is called also Euclidean distance. Some people actually they write something more, usual Euclidean distance. But usual distance or Euclidean distance, same thing. Okay, so this is called the Euclidean distance. But here, make sure that you can prove it. You see that what you will need an inequality. You will need an inequality to prove this triangle inequality. Okay. Now the thing is that here I have taken Rn. If you take Cn, then what will happen? Be careful. If you take Cn, that means n tuple of complex. That means you are taking this. Each zi is a complex number. It's complex number. Look here, if I give this T z omega W. W is take the point. Be careful. Look. This function d value has to be a real, non-negative real. So here you look, it may be square, it may still may come a complex number. Understand? Okay. So that here you'll have to put this mod, not only square. That means here dw has to be defined like this. Otherwise you won't get a non-negative real. Got it? Actually, this symbol you also could use there in Rn. So there I have used this. But for real, it is something. So I will suggest that better use all the time this mod thing on the square. Then for Rn and Cn, you can use the same thing. Again, Cn, this will give you a distance metric. And again is the problem with the triangle inequality. That means triangle inequality, in order to prove triangle inequality, you need an equality. I told you that. It is called Holder's inequality. But you see, if you have know of that inequality, whether that inequality is also valid for complex numbers or not, then you will be able to prove here also. Okay. Now look, this is similar to the Euclidean distance Rn. Often we call it complex Euclidean distance. complex Euclidean distance. In fact, if I am working on Cn, I do not need to mention complexes. Still, by Euclidean distance, it will mean this thing. Okay, that is called the Euclidean complex geometry. Okay, in the metric space, some geometry also comes. It should be expected. Okay, so that here I made a comment that complex and that you should have it. This. Okay, now before that, okay, so that first thing Rn and Cn you get metric. Okay, next thing is that suppose there's an interesting thing. Look at example 3. Page 58. Don't forget it. Okay. He's a very good friend. I'm going to tell you that I have written that. The space given in example 3 is very useful. Often it is used as an easy counter example. What is counter example means? First of all, you take any set X, okay, non-empty set, of course. Okay. Of course, usually in metric space, we take the set having more than one point. If you have only one point, you can think what will happen to the metric. Okay, so that when we consider metric space, we say that X is not only non-empty, X has more than one point. So really definition of metric makes sense, has more than one point. Okay, that is not a singleton set. If you have X is only one point X, then what will be the metric D? That means only you have this, and that definition of metric, it has to be 0. That means it has to be the trivial metric. There is only one metric. So that we do not usually consider this thing. So this is blanket assumption that when we are considering a metric space, X has more than one point. Now look, I give this definition D. D xy equal to 0 if x equal to y. Dxy equal to 1 if x not equal to y. Look, you can easily check that D is a metric on X. Look what I am doing. I am doing, if you have two distinct points, I am always giving the distance 1, nothing else. You said what is special about 1? Nothing special. You could take simply another number, dxy equal to m, where m is, you pick up any number m greater than 0 and you do this. That also you could give. Okay, that means distance between two distinct points I am always keeping fixed. Okay, and this will give you a metric. So G is called a discrete metric. D is called discrete metric on X. And then this pair couplet is called a discrete metric space. Called a discrete metric space. I said I will explain later on. Now look, I said it's a very good friend. Suppose you are thinking about some result, whether it is true on metric space. First you see that whether it is true here. Okay, often something to disprove it may not be true. Yeah, then we look for this counter example, whether this is true. Often this is not true here. Then we say that okay, this result is not general true. I'll have to put some other conditions also. That's why it's a good friend. Okay, apparently it's very simple, but it's very useful. Keep that in mind. Discrete metric space. Discrete metric space. Don't forget about it. Okay. Look, example 4. Already I was giving different metrics on R. Example 4, you have taken positive reals. And here you have given this distance. dxy is this. Again, you check that it's a metric. Again, when you check, you'll see only triangle inequality is giving you the trouble. Other things will be simple to prove. Only triangle inequality. So that when I say verify it, actually verify the triangle inequality. Okay. Right. So that this make sure that in the beginning just examples you read. Okay. Next thing what I'm saying that look on R you have this metric. That means here distance between 2 points can be very large. Can be very large. So in particularly if you look at this collection, now we have done supremum infimum. XY belongs to R. What will be its supremum? Supremum of this set, it will be infinity.
Infinite.
Right? That means what? Supremum infinity means what? That means this set is not bounded in R. Okay? Is not bounded. Okay. Now suppose I have a metric D is not bounded. Suppose I have a metric dxt metric space such that sup of dxy, since uxy is a non-negative number, I can write this is less than this. That means its supremum is a real number. It is a standard notation less than infinity. Look, when you write it, this one, that means left side is a non-negative number. Okay. If it is not a non-negative number, then you'll have to write something like this to indicate it's a real number. Okay. But here I don't need this part. Okay. Here I don't need this part because this is non-negative. So suppose you have this, it means it precisely means this is a bounded set. Okay. Suppose it have this as a bounded set, then we call it a bounded metric. Okay. So now look, that means this metric on this, what I already said, this is not a bounded metric. Not a bounded metric. Okay. But discrete metric, whatever number you choose, 1 or something, another positive real number, discrete metric is always bounded. Okay. But another metric, is it bounded? This metric I have given example 4 on the non-negative reals. Is it bounded?
No, sir.
This is
No,
not
sir.
a bounded metric. Now look, in example 5 I have said, this is very important. Make sure that example 5 you keep in your mind. Later on we will be doing topology that to open sets. And if we have a metric D, that is this. That is XD is a metric space. Then I can define another metric rho. Okay, rho I am giving this defining. Look, I need to write 1 plus. This one doesn't make, is not special. You could take any positive real, but make sure that denominator is not never 0. So this is that's why I'm putting 1. Okay, right? But you can check that you'll have to verify. Rho is a metric. I said so that rho is a metric on X. Now look, difference between the metric D and rho is that about D I do not know whether it is a bounded metric or not. but rho is always a bounded metric because its value is less than equal to 1.
1.
Got it? So that rho is a bounded metric. This is important. Okay. Later on, we'll see that open sets, when you define open set generated by the metric D will be same as generated by metric rho. That means while starting open sets and that we can always take, if we want, to be a bounded metric. So that example 5 you should read it. Okay. First, look at as many as examples you can get for the metric and that. Now I want to prove something very simple thing that is in page 57. Now look, in real line,
Sir, it is less than 1.
it is less than 1. Is it sure? Then fine. But less than equal to 1, if you write, that is not wrong statement. Because it means less than or equal to. So much
Yes,
got?
sir. Yes,
So
sir.
it may happen that it says that. So that is not a wrong statement. Okay. Often we do not bother whether it will be equal or not, we write this. Okay.
Yes,
Got it?
sir.
Now look here. I had the triangle inequality, but look this thing. Is it true or not?
Yes, sir.
How do you
True.
prove it?
Yes, sir.
How do you prove it? You prove it this way. X, you write x minus y plus y, right? Okay, right? Then write this, then use triangle inequality, right?
Yes, sir.
And then, so you have this. Look, x and y are just any arbitrary point. So I can interchange y and x. Look, here I am using it. I told you sometimes unconsciously you do not realize that. Okay. So that this is the opposite sign of this. When I say mod x means what? Either x or minus x, right? So that this will be true. Okay, right? Similarly, do look what I am doing it. That I'm saying if you have this xt is a metric space, then I have this. But that means you have got this thing, but I was calculating basically here I have calculated distance from 0, the origin, right? Okay, but same thing you could do it if I take z, let me see, x minus z minus y minus z. You replace x by x minus z, replace y minus by y minus z. Then you take difference of that, right? The difference will be again same as x minus y, x minus z minus y minus z. It is coming x minus z minus y plus z, right? You got it?
Yes, sir.
So that means what have you got?
Yes, sir.
Distance between x minus z here, a distance between y and z, here less than equal to this. So that if I plug it to geometric space, what I should get? That means dxz dyz, this should be less than equal to dxy. Got it?
Yes, sir.
Look, the proof is basically same. You can look at my proof. What proof I have given here for the real line, same proof is here. Okay, so interchange on that. So that this is the first thing you are getting a small inequality, but it's a very useful inequality. Don't forget it. Okay, this dxj minus dy z mod less than equal to dx. So that means z is disappearing. Okay, right? Well, look here, if you do it, okay, but what does it say actually? Function d. Okay, okay, I will talk about this thing later on. Okay, so discrete metric हो गया. हाँ. Now, just a few minutes. So first, make sure that you understand a definition of metric space. First thing you should know that the metric space is a pair. It is neither just x, not just d. Okay, it is together, a couple, x, d. Okay, and you should know what d satisfies the conditions. That makes sure that you understand. Okay. Now look at here. I want to define basically open sets, but rather ball. I want to define open set to come later. Ball. I want to define ball. How do you define ball? Now look here. When I was having this thing, this always try to have this as a model. If you have something, whether you can say that, whether you can do it, same thing you can imitate in XD. If you can't have something here, don't expect it to have it. But if you have something here, you may not have in YAL here. But if you don't have on R, don't expect you will have it here. Because on R particular metric space, you are not having it. But even after having an R, make sure that you can see that you can imitate the thing. Now look here. Suppose x is any point in R and delta is a greater than 0 number. Here you are considering it as a number and here you are considering it as a point. Then what does it mean? This thing x minus delta, x plus delta. You're saying it is just nothing but open interval centered at x, right? Okay, with both sides
Yes.
distance delta. That means I can write y belongs to R such that distance between y and x less than delta. Got it?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Now, if I do it
Yes,
for
sir.
metric space, look, what will look like that? Okay, of course I won't use this symbol. Okay, but again now if you do it in R point, this is R square you are doing. Okay, if you do it in R square, this is actually it will come a point like x1, x2. Got it? In R square you are doing. This y belongs to R square. So this will be a point y1, y2 like this ordered pair. The distance between this distance means what actually? You should understand.
D of x comma y.
Be, x1 minus y1 square plus x2 minus y2 square root, right? Okay.
Yes, sir.
Yes.
Yes, sir.
That is less than delta. But that will exactly give the ball. That means you will get something like this. This is your point
Okay.
x here. समझ गया? And this is your radius delta. Got it? So that you will basically get all the points. Look, bounded is not there. It is open actually. Like here I call it open interval. I am going for the generalization. So you are getting ball centered at x, the point x, x1, x2 with radius delta. Okay, bounded is not included. So this is a coming open ball rather. Open ball. Okay. Now this will be the better thing to do. In XD, if I want to have this concept of open ball, then how will I write it? Okay, just let me see. Look, just imitate this definition. So take a point x belongs to x I want to define this ball. Centered at x like this with radius delta. Then what I should have the definition? I should have point y in place of r square. It will be x again. Okay? And
Yes, sir.
this will be dxy, right?
Yes.
dyx less than delta. That's exactly the thing. This is called the open ball. This is the definition. I've explained that in page 59. That this is called the open ball centered at x with radius delta. Some people call it r. Here I have taken delta because I was comparing with your interval with radius delta. समझ गया? Right?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Exactly, I am copying you what I got in r square. Okay. Now, if I take this, look, closed ball. Okay. Then it will go cx delta. Then it will be this thing, right?
Yes, sir.
Yes,
Equal
sir.
to हो जाएगा.
Yes, sir. Equal
Suppose
to.
if you
Yes.
take the closed ball. Similarly, so that I can define your closed ball, what I will do, cx delta, here I will put less than equal to delta. समझ गया? And instead of open, I will write closed ball. समझ गया? What? So that this is this Wacom I'm doing it. Something you look at the plane. Plane is nothing but r square. So first thing you do, what I am going to do in metric space throughout the study of metric space, see whether you can do it in r square. Even you don't need to look at r cube. If you are working with your laptop, you look at this on the screen whether you can do it. If you can do it something in r square, then you expect to do it on a geometric space. It may not be always true, but if you can do it on this, on the screen of your laptop, and that is on r square, then don't think you will be able to do it in a geometric space. You won't be able to do it. So that, but the technique, the thing is that what is the advantage? Then if you have a result on a metric space, first is that whether you can do it in r square. How you try to prove it? That you should know because you did something in your undergraduate in r square. You see whether you can prove it on r square. If you can prove it in r square, then you see that whether that proof works also on xd or not. Okay, so that's the idea. First thing you make sure while studying metric space whether you can do it on r square on the screen of your laptop. Okay, that you can do. That is very important. Okay, so that here, so that I have defined closed ball, open ball. The next thing is that means interval like that in R. You have this thing. Open interval centered at x, closed interval centered at x. Similarly, open ball, closed ball. Also, you see that if you take delta prime less than delta, then obviously this will be contained in this. The same thing here, it should happen that if you have this s was positive, look, radius I am taking, delta is always a positive number. If you have this, then I have from definition, I will have this for a geometric space. It follows from the definition. It will be contained in this. And sorry. ठीक है? But here you look, be careful. Here, when we are having this, if delta prime is strictly less than delta, then this interval will be contained strictly inside this. That means it will be bigger. But in a geometric space, they may be equal. They may be equal. So how it can be equal? That's why I'm saying be careful about this metric space, XD discrete metric space. Look, if you have Discrete metric. Okay, recall that dxy equal to 1 if x not equal to y, and dxx equal to 0. That means dxy equal to 0 if y equal to x. If I don't give this, then I won't give the definition of the metric. X not equal to y, this. Now you tell me what is bx1 here. In this, you just tell me what is bx1.
Y belongs to X.
So
Such that
single point
G
zero.
of
Only this point,
Single point zero.
x.
X. Yes.
And then what will be this? That will be also single point x.
X.
yes.
Then but they are same. Okay. So all I could say is less than contained in that. It's not strictly contained. Understand? Okay. So this
Sir.
is the first. Say again.
Yes, sir.
That is the first use of discrete metric space. I have this. Again, I'm repeating it. I'm saying this is contained, but it may not be strictly contained. It may not be the bigger than this thing. They may be equal. So look at this. Similarly for C, look, Cx1 will be what? Let me tell you. What will be Cx1?
Complete set X.
Whole set X will come. Okay. But then Cx2 will be what? That will be also whole
Complete
X.
set X.
So that here you may be equal. Understand? Okay. On the other hand, you look Cx half. That will be X again.
Singleton X.
But here you look. That the closed ball and this thing, they are equal actually. In fact, even closed ball may be equal to open ball. Okay. So that don't ignore discrete metric space. Think about something, discrete metric space. Okay. Right. So that I think next class I will take on Monday. Monday है ना? तुम्हारा एग्जाम कब है?
19
से
to 23.
19 to 23.
Yes, sir.
Yes, sir.
Let me look at my calendar. That means I'll have 2 more weeks. Okay. But I am thinking, who is your class representative? CR?
Shraddha.
Yes, sir.
Huh?
Yes, sir.
Yes,
Good
sir.
afternoon, sir. My name is Shraddha, sir.
Okay. I will send mail to everybody, but I think you send me separate email to that. Because I will send the notices to you and that. So you
Yes.
should have the responsibility to tell your classmates. And you have the
Yes, sir.
exam 9 to 23, but I am telling you that if you want to lessen your burden, you can have my exam after 23 also. Like
Yes, sir.
Saturday 25th, if you want. Okay.
Yes, sir.
That I am giving you the choice. That you don't necessarily don't have to take the exam between 19 and 23. But as class representative, you should talk to your classmates. Okay. So that nobody should complain that you didn't take the exam in the scheduled thing period, or later on I had problem these. Okay. So that you
Yes,
should
sir.
send a message, whatever, through WhatsApp and that to your friends, classmates.
Yes, sir.
So that
Yes, sir.
you can see, even in place of 25th, you can have another date, but not too late. Okay.
Excuse me,
sir. Too late, then I will have the problem in starting the classes again. ठीक है?
Yes, sir.
Excuse me, sir.
हाँ, बताओ.
Sir, on 25th we have computer exam.
25th you have computer exam. दे तुम बताओ. मुझे कोई
Sir,
problem.
can you take on 26?
I think you
Sir, we
discuss
will
among
discuss.
yourselves, and then
Yes,
you
sir.
don't need to tell me right now. Okay.
Yes, sir. Yes,
You
sir.
discuss
Yes,
among
sir.
yourselves, then you let me know. ठीक है?
Yes, sir.
Okay. So
ठीक है
I
सर.
will class on Monday, right?
Yes,
Yes,
sir.
sir.
Yes. So you can tell me. It is your choice. I am just telling the thought Saturday and that. It's fine. You
Yes,
can
sir.
give me any other date. Okay. But it's not too late. समझ गया?
Yes, sir.
Okay.
Yes, sir.
Bye.
Okay,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.